Hello, this is Xiaoping Xiao, a professor of mechanical engineering at the University of Iowa. Today, I will talk about the model-free control synthesis of complex tasks in partially observable and dynamic environments. The motivation of this study is in most real-world applications, the environment actually is partially observable. So in that case, the agent may not have a complete knowledge about its environment. So the Markov decision process, a framework called MDP, is not suitable. So we have to adopt the POMDP, that's the partially observable Markov decision process. In addition, and the environment, action, observation alternatives should be considered. And another motivation is most of the study only focus on the simple go-to-go task. But however, the complex task need to be using formal language, like high-level logical language to express. So the objective of this study is we plan to develop a model-free approach to solve the reinforcement learning motion planning problems for agents to accomplish the complex task in partially observable environments. And there are some studies already proposed or developed reinforcement learning approaches for POMDP problems, like the point-based value iteration that's using the dynamic programming, and also some model-free approach using the DQN. But however, they mainly focus on the simple go-to-go problems, consider the complex tasks. And for complex tasks, actually, mostly consider in MDP problem, people using linear temporal logic, LTL, to express the task and then convert to the automata, finite state automata, and use the model checking to check whether the task is accomplished or not. So this is mainly focused on the MDP. So our contribution is we're using the probabilistic labeled POMDP to represent the partially observable and the dynamic environment. So we consider both static and a dynamic event in the environment. And we also use the linear temporal logic language to express the complex task in POMDP problems and convert it to limit deterministic generalized Boochi automata. So this is one kind of finite state automata. And then we generate a product of POMDP, and LDGPA. So then the problem is how to solve this product POMDP. So we proposed a model-free approach using the DQN with the implementation of LSTM, a kind of RNN in the Q network architecture. And we also consider two scenarios about whether the agent is aware of the task or not to solve this proposed problem. So for the probabilistically labeled POMDP, and it is mathematically can be defined with a tuple, include state space, action space, transition function, initial state, and the reward function. So that's a pretty general definition in Markov decision process, also in the POMDP. And in addition, so we have the observation space, the observation probability, and the pi here is a finite set of atomic proposition, and the L is the label function to give some states with the labels, and those labeling actually have the probability. So if some particular state is only labeled with one label and the probability is 1, so this is the static events. Otherwise, if more than one labels are assigned to a particular state and the summation of the probability equals to 1, so this is the dynamic events. For the linear temporal logic, actually, it's a high-level logical language can be used to describe the complex task. Instead of, in addition to the Boolean operators and the temporal logical language actually has the temporal operators as well. That's include the next, until, eventually, always. So then we can use linear temporal logic language to express the complex task, especially, for example, surveillance problem visit the one state then another state, and repeat infinitely. So the LTL formula, after express the complex task, the LTL formula actually can be converted to the finite state automata. So here we use the limit deterministic generalized Booch automata. So that's the LDGBA. And definition of LDGBA is it has state space, and the sigma is a finite alphabet, and that's include the symbols as the input to the automata, and the delta is the transition, state to state transition in the automata. We have initial states, and also F is a set of accepting sets. Each set include a number of accepting states. So for the automata, the input is a word, and that's the sequence of the symbols. And actually, relative to the POMDP problem, that should be the symbols. Actually, they are the labels. And such a word results in a sequence of states based on the transition function, based on the transition from state to another state. So if for such a sequence of states eventually encounter with the accepting states, we say that there's a sequence of states that actually satisfies the this LDGBA acceptance condition, or we say the LDGBA accept the given word. Usually in computer science, and researchers using the model checking to check whether the word is accepted by the finite automata or not. So therefore, and from the objective, after we introduce the POMDP and LTL, and also the automata, so then we define the problem. So giving a the POMDP and the complex task, this POMDP describes the partially observable and the dynamic environment, and also the complex task expressed by the LTL formula, and then convert to the LDGBA. So the objective is we want to find the optimal policy on the POMDP, and such that the generated path can complete the task and also satisfy the acceptance condition of the LDGBA. So this is the first definition of the problem. So how to solve this problem? And after we define the POMDP and also the automata, here is LDGBA. So then we do the product, we do the condition product. Yeah, this is the POMDP describe the environment, and LDGBA convert from the LTL formula and define or describe the task. So then we do the product, and the product include the product state space, and the transition would be the action space from the POMDP plus the epsilon transition from the automata. So epsilon transition means there's no symbol for the transition in automata. And correspondingly, we can propose or develop the transition function, the initial state, the reward function, observation function, and also the acceptance sets in the product POMDP. The product POMDP actually is one kind of POMDP. So to our assumption is so we assume, yeah, we don't consider infeasible task. So we assume there's exists a policy on the product POMDP. So a generated path, they are encountered with the accepting sets. So then satisfy the acceptance condition of the product POMDP. And borrow the statement from the product MDP, and we know the optimal policy on the product POMDP actually is equivalent to the optimal policy on the POMDP, and also satisfy the LTL specifications. So that means as long as we can find the optimal policy on the product POMDP, so then we find the policy on the POMDP, and also the complex task is satisfied, is accomplished. So therefore, we can redefine the problem. The problem redefinition would be after we constructed the product POMDP. We just need to find the optimal policy on the over the product POMDP to maximize the expected return. So the solution would be using the reinforcement learning. So here we use the DQN. So back to the DQN on the POMDP or the POMDP, And the DQ and the Q network actually include RNN because the input is a sequence of the observations. So for the partially observable environment, the agent will make the decision based on the current and the previous observation. So that's the observation history, and which is a sequence of observation. So therefore, and the input will be the sequence of the observation. So we need RNN to process the this time series data, and then using the fully connected layer to predict the Q value. So this is the Q network architecture in DQN we're going to use. And this is only for the POMDP. So we can extend such a DQN approach to the solution to solve the product POMDP. So for the product POMDP, since this is the product of POMDP and also the automata, so therefore we need two inputs. We need two inputs. One is the history of observation, as usual. Another one is we call it the task recognition history. So that would be the history of the state transition on the automata. So assumption is the agent can precisely perceive the labels based on the labeling probability function. And those labels, they are the symbols of the word as the input to the automata. But in addition to consider the agent be aware of the task, and we'll also consider the scenario for the agent who is not aware of the task. So those two scenarios. For the first scenarios, if the agent knows the task, so that means the agent has the complete knowledge about the automata. So therefore, using the labels, receive the labels as the symbol of the word, and the agent can identify the state transition, can identify a sequence of automata states. So therefore, in addition to the observation history and the sequence of automata state will be another input. If the agent is not aware of the task, so then the agent doesn't have knowledge about the state transition in automata. So in that case, and the agent has to use the state label as another input. Architecture of the DQN for solving such a problem would be similar, but we have two sequence. And for the first scenarios, if the agent knows the task and knows it has a complete knowledge about automata, so therefore, in addition to the sequence of the observation, there is a sequence of automata state as the second input. And I would like to say that because the state transition in automata is not as frequent as the state transition in the POMDP. So therefore, the length of those two sequences actually they're different. So that's why, and we use to separate the LSTM to process those two sequences, and then to get the Q value. For second scenarios, and the sequence of automata state would be replaced by the sequence of the state labels because the agent has no knowledge about the task. So simulations, we will present the two simulations. The first one is 10x10 grid world workspace, and we transition probability is 0.9 to the intended direction and 0.1 to other directions. Observation probability is 0.9 for the current state and 0.1 for the neighboring states. And the B is obstacle states, and the C is the trapping states, that's the unsafe states. So the task for the agent is visit states labeled with A, and then B, and repeatedly, infinitely. And so the LTL formula would be always eventually A and eventually B, and always not C. So this is LTL formula and convert to the automata LDGBA. And we consider two scenarios. One is the agent knows the task, has the complete knowledge about automata. So then the Q state as additional input in addition to the sequence of the observation. So this is the start state, and the agent is going to visit A first, and then from the A visit the B. That's the one round. Second round from the B to A and back and forth. And also we consider second scenarios, and the agent has no knowledge about the task. So therefore, labels, a sequence of labels would be the second input in addition to the sequence of observation. So after we find the policy, so the path generated would be showing here, start from start state, and then go to state A, and then from A to B, and first round, second round, from B to A, and so on. And here before we consider only the static events, so that means 100% labeling probability on A on the given state, B on another state. But here we consider dynamic event. That would be the for example, for those states, and there's a 90% probability labeled with A, 10% probability labeled with B, and similarly 90% probability of those states labeled with B, and 10% was labeled with A. So we also consider use Q state or the label as the input. So here is after we find the policy, respectively, we generate the path. So for the Q state as a second input, so this is the agent start from initial state to the states mostly labeled with A, and then back to the states mostly with B, back and forth. And this is the path generated using the label as the second input. So this is the first simulation. Second simulation will consider office scenarios, include 4 offices and a storage room, supply station, and the printing room. And we'll also consider transition probability as well. And in this case, and we consider 2 tasks. One is the turtle boat visit the printing room and collect the documents, and then deliver to the either office A or C, and repeat this infinite time. And task 2 is on the top of task 1 after delivering the document, and then the agent must go to the supply station for recharge, and then repeat the task 1. So those are the LTL formula with the corresponding automata. And here we only consider the agent knows the task, so it has the complete knowledge about the automata. And for the observation space, and the agent can observe hallway and the wall, door, the window, and also the table, the paint on the wall, and the flowers by the wall. So those are the observations the agent can observe. And here we're assuming the agent can only observe a single direction. So therefore, that means that we do have the probability for the observation. For example, in the office B, the agent has 50% to observe the wall, and 25% observe the door, 25% to observe the table. So the simulation results is for the task 1, the agent start from the office B and go to the printing room to collect the documents, and then deliver to the office C. So that's task 1, first run, and then can repeat. And the second task start from the office B, go to the printing room, and then deliver documents to the room C, and then go to the supply room for recharge. So that's the task 2. And we see there's many motions back and forth. That's because of the transition uncertainty and also the observation uncertainty. Okay, so in this study, we use the LTL to express the complex task, and also use probabilistic labeled PMDP to express or to describe the partially observable and the dynamic environment. And we do the product between the PMDP and LTL induced automata. And so then we can find the optimal policy by using the model checking as well as the reinforcement learning. And we develop a model-free reinforcement learning method. And for this study, we would like to thank the support from the NSF and also the Department of Education. Thank you.